Hello everyone. Again, I want to remind you to please mute your phone, and I know the presenters will be using their mute function as well. My name is Alan Hahn. I am the Business Development Manager at Dragun. And if you have questions during the presentation today, we're just going to ask that you email them to me. My email is up there on the screen. It's ahahn@dragun.com. And then I'll be monitoring those emails during today's presentation. I know that there are many people that were here last week as well, but this is the second of our two webinars. First one was on how to build a robust conceptual site model to get your arms around the issue. After you've developed your conceptual site model, you're now prepared to look at some of the various remediation tools that my colleagues will be discussing today. We have participants in both the United States and Canada, and presenters from both the U.S. and Canada. Matt Schroeder is a professional engineer in our U.S. office, and Andrew Timmick, a professional engineer in our Canadian office. And with that, I'm going to turn the presentation over to Andrew to begin today.
Thank you, Alan. As Alan just mentioned, I'm Andrew Timmick. I'm a professional environmental engineer with Dragun, and I manage remediation projects in Canada. Sorry, there I am. I am a licensed environmental engineer in Ontario, and like I just mentioned, I manage remediation projects in Canada. So this is our second webinar in the two-part series regarding recent developments in site remediation, and then, as Alan just mentioned, last week my colleagues Dr. Mike Sklash and Chris Perry focused on techniques to get a more robust conceptual site model, which really focused on how to get your arms around a contamination problem. Today our focus will be on how to attack those problems as we discuss advancements in the field of soil and groundwater remediation. So this is going to be a very informal webinar, and we have a lot of material to present in a relatively small window of time. So without further ado, we'll jump right into our first topic, and that is in situ chemical oxidation, which is also known as ISCO. ISCO is a common remediation technology that we've experienced varying rates of success with. In case you don't know too much about ISCO, I'm going to give you a quick and dirty background. Generally speaking, ISCO is the application of an oxidizing agent to a contamination plume. And this is typically achieved by injecting the oxygen over a grid of direct push injection points, as you see in these two photos, or wells over the entire areal extent or distribution of the plume. The oxygen acts as the electron acceptor in an oxidation reduction or redox reaction that transfers electrons from a contaminant to the oxidizing agent. The result of the redox reaction is a conversion of the contaminant to an inert or benign compound such as CO2 or ethane, depending on the contaminant of concern. Common oxidants used in the ISCO industry include Fenton's reagent, which is basically just iron and peroxide, percarbonate, persulfate, and permanganate. So the two photos you see on the slide are of a remediation site we have in southwestern Ontario. What you see here are injection rods that were pushed to the depth of impacted soil and groundwater, and the oxidant, persulfate, was injected to oxidize the petroleum contamination that was caused by a previous major leak of gasoline and used oil from a faulty underground storage tank. At this site, we were able to reduce chemical concentrations in soil and groundwater below the standards at 90% using ISCO methods alone. So what's changing in the ISCO world? Well, when ISCO was first employed for site remediation, the old way of thinking was to simply flood the subsurface with the oxidant solution, which was usually Fenton's reagent, and basically just hope it works. The problem with the original ISCO methods was that Fenton's reagent resulted in a very fast and very exothermic reaction, meaning lots of heat and lots of gas was generated. New oxidants are designed to work slower, more efficiently, and over a longer period of time without these dangerous exothermic reactions. So this group of photos are of another injection site. This one's in Western Ontario, where chlorinated solvents were leaked to the subsurface from a former industrial degreasing operation. In the two photos on the left, you see the injection of permanganate, which has a distinctive purple color, if you see the two photos on the right. Permanganate was found in groundwater in a nearby well and in soil from a nearby boring, both adjacent to an injection point. Permanganate gained some fame in years. Make note that this example I'm about to give you is not a Dragun Corporation, but to absorb the oxidant and injected a large volume of permanganate into the ground. The site was in the proximity of a large water body, and the permanganate was spotted by locals seeping out of the soil across the shoreline into the lake. This led to a very expensive emergency action to neutralize the permanganate plume. And this type of problem can usually be, once again, avoided if the site is properly characterized. So, what have we learned in recent years? Well, basically, ISCO is fundamentally a contact sport. You must get the reagents to where the contaminants are. In theory, this sounds like a very simple concept, as you may infer from the injection schematic on the right side of this slide. But in practice, contact between oxidant and the contaminant can be incredibly challenging. And we'll discuss this further in the next few slides. We've gotten better in a couple of ways. As we learned during last week's webinar, recognizing that better characterization is needed for remediation than just a traditional investigation is key. We can now employ high-resolution site characterization, such as MIP, LIF, and HPT, which you would have learned about during Mike and Chris's presentation last week. And we can also attain more precise injection depth intervals using specialized injection tools. And we'll learn a little bit more about that in the next slide. So a good thing to take note of here that I'm going to mention is if ISCO is determined to be the most feasible remediation option for your site, you can greatly increase your probability of success of the ISCO program by conducting a detailed pilot study or bench scale testing of an injection program to determine the best parameters for your specific site. From this, you can determine the optimal injection pressures, oxidant mixture, radius of influence, natural oxidant demand of the soil, among many other things. From our experience, the most common findings from our pilot study is that low pressure injections using proper lateral injection tooling is usually required to meet remediation goals. So on that note, let's discuss some of the specialized equipment for in situ injections that are available on the market. The image shown on the top left corner, right here, kind of looks like a metallic arrow of this slide, is a disposable injection tip. This was the original tool used in ISCO injections. Basically, this disposable tip was advanced at the end of a string of steel injection pipes down to the bottom of contamination. The drill rods were then raised slightly to release the tip, leaving an open end at the base of the injection rods. The oxidant was then flooded in the area under the assumption that the oxidant would mound upwards into the contamination zone. This method is now somewhat obsolete because of advancements in injection tooling. So the other four tools that you see on this slide were developed in recent years to aid with lateral injection of oxidants. These tools allow the oxidant to be applied over a specific depth range or zone of contamination, typically between 2.5 to 12 inches. Some lateral injection tools are activated via pressurization, which is shown in the two photos on the right of the slide, and others are simply an injection screen in a retractable sleeve that is opened by pulling up on the drill rods. These are the two long injection tools on the left side of the slide. We've observed some noticeable improvements in injection coverage when using the sleeve-type tooling. The pressure-activated tool also had some promising results, but were subject to frequent mechanical malfunctions, from soil grit clogging to perforations. So now we're going to jump into some of the considerations for ISCO technologies. During these next few slides, we're going to chat a little bit about some of the specific considerations for ISCO if you're thinking about using this technology for your site. The conceptual site model that you see in this slide is for one of our sites in Western Ontario, where the groundwater table is very deep, approximately 20 meters or 65 feet below grade. A large fuel spill from an old UST nest left a large amount of contamination in the vadose zone, also known as the unsaturated zone. So the applicability of ISCO relies on the radius of influence. This is the radius around an injected oxidant where contact with the contamination is expected to occur. The minimal acceptable radius of influence is usually between 3 and 4 meters for an efficient remediation project, just as a rule of thumb. This range of radius of influence is not typically far-fetched when injecting below the water table, because here, the majority of the void spaces, soil grains, is saturated with water, and this can help disperse the oxidant. Injecting into the vadose zone or the unsaturated zone is impractical, as these void spaces here are not saturated, and this would reduce the spread of the injected oxidant. There are also technologies available to mix chemicals into vadose zone soils, and my co-presenter, Matt Schroeder, will discuss these in more detail later. So another consideration for ISCO technologies is it's more of a hurdle than anything for ISCO injections is the presence of non-aqueous phase liquids, or NAPLs. NAPLs are high concentration liquid contaminants that are commonly referred to as free product. NAPLs are characterized as either L for light NAPLs, which float on the water table, or D for dense NAPLs, which sink to the bottom of the aquifer. The quick cliff notes for NAPL mobility, since there's a lot of science out on this now, is that a NAPL dissolves gradually into the saturated zone until a quasi-equilibrium is reached between the layer of free product and the aquifer. Also, once a source is removed, NAPL requires other processes to help it move or degrade. So NAPLs really pose a significant problem for potential ISCO sites because, as we just discussed, oxidants are best applied to contaminants below the water table that are in the dissolve phase. Now, you can inject ISCO below L NAPL or above D NAPL and reduce the contaminants in the dissolve phase, but the NAPL will only redissolve in the groundwater gradually until that quasi-equilibrium state is reachieved. So for these reasons, ISCO is definitely not recommended for sites with NAPLs. So just a quick warning is that some remediation contractors that you may deal with may still try to sell you that they can remediate a site where NAPL is present. But we strongly recommend looking at other technologies other than ISCO if NAPL is known or even suspected at your site. Another thing when considering ISCO for your site is the potential for daughter products. So basically all contaminants break down into other, typically less toxic compounds during the redox process. This slide shows an example of how a chlorinated solvent would break down in the redox process. This is trichloroethylene, or TCE, reduction chain. TCE is a carcinogenic or cancer-causing chemical commonly found in industrial degreasing operations. Generally speaking, TCE, before being reduced to its inert form of ethane or ethene, will convert to vinyl chloride, which is considered a much more toxic and much more mobile contaminant. The creation of daughter products like vinyl chloride and their potential detriments to the environmental surroundings at your site must be considered before starting an ISCO program. So in situations where soil and groundwater contamination is shallow, we start having to concern ourselves with subsurface infrastructure and utilities. The application of ISCO will cause metal to rust in water. This could cause costly damage to underground utilities. One example of a subsurface rusting failure in Canada was an ISCO injection program that was carried out near an underground storage tank nest. The oxygen bled into the perched groundwater in the backfill around the tanks and rusted the bolts that secured the tie-down straps that keep the tanks from being buoyant. The oxygen rusted out these bolts, and the buoyant force caused the tanks to slightly rise and rotate underground, and this broke the fuel distribution piping, and this caused a catastrophic loss of fuel into the subsurface. So the take-home message from this slide is that ISCO injections will not only oxidize contaminants and can actually amplify a problem rather than solve it. Another issue with shallow injections is that the trenches around subsurface utilities can also be considered a preferential pathway for the injected oxidant. We're going to talk about that a little bit more in the next slide, which is about preferential pathways. So preferential pathways are zones of higher hydraulic conductivity in the subsurface that can lead to losses in injected oxidants. So for example, if a contamination plume is located within a low conductivity soil setting like a silt or a clay, but there's a higher conductivity soil setting adjacent to it like a sand, the oxidants typically delivered at high pressures could bleed into the undesired high conductivity zone. Preferential pathways can be naturally occurring, like the photo on the left, such as the conceptual photo on the left, and or man-made, such as the conceptual site model on the right side of this slide. So this conceptual site model you see on the right is from the site we introduced at the beginning of this talk, where we injected persulfate to remediate 90% of the property. Remediation at this site previously included a substantial excavation with high purge rate dewatering, and they did not conduct a detailed site characterization, the importance of which we learned last week, and they were unaware of the large L NAPL plume floating on the water table. The high rate of dewatering caused the NAPL to smear below the water table, which you can see here as a purple dashed zone on the right slide, right conceptual site model on this slide. And as previously mentioned, 90% of the site was successfully remediated using ISCO methods. However, the final 10% was overlain by a significant area of backfill that you can see as gray in this slide. and a large diameter pumping well surrounded by high conductivity gravel, which is the darker gray. And this rendered ISCO relatively useless at this site, and we had to reevaluate our options. Heterogeneities in soil also lead to common post-ISCO remediation effects that is commonly referred to as contaminant rebound or matrix diffusion. And on the next slide, my co-presenter and fellow environmental engineer, Matt Schroeder, will show you a brief video on the effect of matrix diffusion.
So the video I'm going to show here was developed by Colorado State University, and what they did is they developed a flow cell where there's aquifer and aquitard material interbedded, and they used a green dye to simulate a contaminant within the aquifer and showed a little bit of how it acted within the aquitard layers. So I'll go ahead and start the video here. The flow is from the left to the right, and what you'll see here is that the darker layers are the bentonite zones within the aquifer. The lighter sand is the lighter color is the sand layers. So here you see them flooding the zone with the dye from left to right, and as the video runs here, you'll start to see the edges of the bentonite layers start to get a little green as it starts to permeate into the clay layers. And somewhere along in here, they'll stop the dye and start clean water back across the aquifer. So this would be when the remediation occurs. And you can see, now that even clean water is moving across, you can see the green dye still leaching out of the clay layers, and how on the edge of the clay layers we've still got significant amount of green that ends up out into the aquifer layers. So I think it's a good visual illustration of how matrix diffusion works when you've got interbedded high and low permeability materials. And this goes on for another couple minutes, but there's really not much more to see. So I'll go ahead and stop it here and turn it back to Andrew.
Thanks, Matt. So just a side note here before we get into bioremediation is that we've also learned more about how ISCO affects bioremediation. And the old thinking was that ISCO would kill off any of the natural organisms that may aid in the bioremediation of contaminants. But what we've learned is that microbial populations are typically very hardy and come back quickly, even within months after an ISCO treatment. So with that kind of ends our ISCO remediation talk, and I just want to give you guys a quick reminder that if you have any questions during the presentation, go ahead and email Alan Hahn, and we'll try and get to your questions at the end of the webinar if we have time. And his email address is ahahn@dragun.com. So this brings us into our next topic, which is bioremediation, more specifically in situ bioremediation. And this is a technique that is commonly used either in low concentration groundwater plumes or at the tail end of a remediation program as a polishing technique to finish off a remediation program. In the right conditions, natural occurring organisms can significantly degrade a contaminant plume. So for example, an oxygen-rich aquifer can promote the growth of organisms that degrade gasoline plumes or diesel plumes even, and an oxygen-deficient aquifer can promote the natural attenuation of chlorinated solvent plumes. These photos that you see on this slide show the injection of an oxygen-releasing material used to provide a long-term oxygen source which artificially increased dissolved oxygen in the aquifer. And this technology was employed at the downgrading end of a plume near the property line to promote biological activity in the impacted groundwater that had migrated off-site. These types of injections provide a relatively inexpensive enhanced dissolved oxygen source that typically lasts between 12 and 18 months. So what's really changed in this field is when enhanced bioremediation was first employed, the thought was that bugs will do their thing, for some contaminants at least, if you just give them a push in the right direction. What we'll see in the next few slides is that, although this may be the case, a more robust site characterization is necessary to evaluate the applicability of enhanced bioremediation. So another option for enhanced bioremediation of dissolved phase plumes is employing oxygen emitters. Excuse me. And Waterloo emitters is a popular brand of oxygen diffusers that is gaining some traction in the remediation industry. Now, emitters generally rely on diffusion to add dissolved oxygen to an aquifer. And the common misconception is that Waterloo emitters are the same as an air sparge system, but that's not the case. Air sparge relies on the high rate pumping of air into a submerged screen and is often coupled with soil vapor extraction. Emitters really rely on diffusion to add an increased amount of dissolved oxygen into the aquifer. The diffusion process from emitters occurs from high concentration oxygen, which is carried through the tubing wrapped around the submerged emitter structure. High concentration oxygen permeates through the plastic into the lower dissolved oxygen concentration groundwater. The plastic tubing on the emitters structure is shown in the image on the right of the slide, and on the left is a schematic of a typical Waterloo emitter setup. The difference between using diffusers and injecting an oxygen releasing compound, as we saw on the last slide, is that emitters are a continuous source of elevated dissolved oxygen, while injected compounds vary in dissolved oxygen concentration with time. Also, emitters aid with the vertical distribution of oxygen, whereas oxygen injections are limited by similar challenges that we discussed during our talk of ISCO that we discussed earlier. Emitters are fed by compressed air or pressurized oxygen. Although our experience dictates that pressurized oxygen works best in high concentration plumes, you can also use compressed air, which is a cheaper option if you have a low concentration plume that you're kind of just trying to use some polishing techniques to get to the end of your remediation program. Another consideration if you're going to use an oxygen supply for an emitter system is that oxygen must be restocked periodically, and this is typically every month, but there's minimal operation and maintenance involved to operate these types of systems. So in these photos that you see in the slide are from an installation of a Waterloo emitter fence employed at a site in Western Ontario. Originally at this site, a Waterloo emitter fence was installed perpendicular to groundwater flow to cut off the flow of a gasoline plume before it migrated off-site. We're still observing exemplary reductions at this end of the plume. Even more recently, a second row of emitters has been installed at the upgrading end of the plume to aid with on-site remediation of dissolved phase contamination. Some of the lessons we've learned in the bioremediation industry is that the time-released remediation compounds, such as the oxygen-releasing materials that you would inject, are cheaper yet more of a short-term option. And emitters, while more expensive, provide a continuous dissolved oxygen source. Another thing is that alternative chemicals are now available for contaminants such as chlorinated solvents that degrade in anaerobic conditions. An example of one of these chemicals is hydrogen-releasing compound, which you can inject similar to ISCO or oxygen-releasing compounds. So a better site characterization like those discussed last week can get you closer to a successful bioremediation program. For example, we can conduct bioassays, and we can also gain site-specific knowledge of the geochemistry at a site to determine what biota is native to the area and if there are other chemicals present that could promote or inhibit bioremediation. Another thing is bioaugmentation is being carried out to supplement bioremediation, and this is accomplished through artificially inoculating the groundwater plume with biotics that are known to consume contaminants. There's also significant advancements in the area of trap and treat type bioremediations, and Matt Schroeder will discuss these shortly. So one last case study before I pass the mic over to Matt, very briefly, where we employed another form of long-term oxidation source. At this site in southwestern Ontario, we had a shallow gasoline contamination issue in both soil and groundwater that remained in a wedge that we could not excavate because of physical constraints at that site. Here we employed a large diameter auger system that we advanced to the bottom of the impacted soil at the upgrading end of contamination. We then backfilled the large auger holes with a mix of high conductivity stone and the persulfate oxidant. We relied on the natural flow of groundwater to carry the oxidant to the downgradient soil and groundwater contamination. This method resulted in significant reductions in groundwater contamination. However, the soil matrix diffusion that we discussed a little bit earlier proved to be too significant. We were unable to reduce concentrations in the soil to below the required standards. So with that, I leave you to my colleague Matt Schroeder, who will now discuss some advancements in the fields of high-strength source removal and plume capture.
Thanks, Andrew. Hi, I'm Matt Schroeder. I'm a senior environmental engineer here in our Farmington Hills office. And I'm going to talk, as Andrew said, about a couple other areas where there's been some advancements. Before I get onto that, I'm going to give you one more reminder that if you do have questions, to email them to Alan Hahn, AHAHN @dragun.com, and we'll address those at the end of the talk here. So most of you have probably experienced that regulators really are focused on source control, and typically that's meant dig and haul. And you know, that's still probably the best option in a lot of cases, but there are times when transport and disposal costs can be prohibitive, and in those cases, the feasibility of other approaches starts to look better. So, for example, one of our projects, we've got a 6-hour drive to the closest applicable landfill. When you're looking at a 12-hour round trip for each load, the dig and haul cost can escalate quickly. So one of the things that's gaining some traction for high-strength source areas is soil mixing. And this isn't a new technology. You know, excavators and augers have been around for a long time, but what it does is it combines those physical means with some of the other methods that Andrews talked about earlier with ISCO and bioremediation and things like that. So the augers, which are showing in the schematic on the left, can be up to 10 feet in diameter. And what they do is, as they auger down, you can add reagents and mix it right in with the soil within the augers, so that you get a good contact between the soil and the reagents. And some of the advantages of using the augers is, number one, they can typically go a lot deeper than a traditional excavator without having shoring or benching to get down there, or sloped sidewalls. And secondly, oh, sorry, I already talked about that. You don't need sloping or shoring. So on the right is a more traditional type of soil mixing, where they're using an excavator with a head on the excavator to mix the reagent in with the soil. And this is typically used for shallower sites where the contamination is near surface. And again, you know, typically both of these would be where transport and disposal cost prohibitive. Another method that is starting to gain some traction in treating source areas is treatment. And the example I'm showing here is electrical resistance heating. And in this technology, they put electrodes into the ground. You can see them on the picture here on the left. And the electricity is conducted between the electrodes through the soil. And as the electricity passes through, the resistance of the soil heats the soil and drives off volatile contaminants. And it's typically paired with SVE, and then the SVE is used to capture the contaminants and then treat them and discharge them at the surface. This isn't the perfect technology for every site because it has a relatively high unit cost, but the removal efficiency are amazing with this, typically higher than 99%. And the other advantage that you get with the thermal treatment is the short time frames, and typically less than a year for thermal treatment. One of the downsides is it's only really applicable to volatile contaminants. So anything non-volatile like heavy organics, metals, PCBs, things like that, those aren't really going to be affected by thermal treatment. We're actually going to be piloting a thermal system at a site where we have some really high TCE impacts within the next few months. The next thing that I'll talk about, some new ways of thinking, is about plume capture. So for a long time, whenever there was a plume migrating off-site, we used pump and treat systems to stop the plume. And it's typically included hydraulic capture, above-ground treatment, and then discharge to either a sewer system or a surface water. The system we're showing on the left here or on the right here is one of our projects. These air strippers were installed before we were working on the project, but they're still operating today. And so this is the type of O&M that people run into with long-term pump and treat systems. Over the past couple of years, we've had some new tools that have been developed that may make a more cost sense in a situation like this. The first is trap and treat products. And trap and treat products are an injectable form of activated carbon that has a reagent embedded within the carbon granules. There's a lot of brands out there of this. You'll hear the Boss products. Regenesis has their own product called Plume Stop. Tersus has a product. I'll refer to the BOSS products just because those are the ones that we've used most often, although the other suppliers, their products are very similar formulations. So there's generally two types of these products. One is for hydrocarbons, and that's where the carbon is generally infused with oxygen and electron acceptors, and that helps to promote enhanced bioremediation. And that's the BOSS 200 product. And for chlorinated solvents, it's a BOSS 100, and that's generally where zero-valent iron is in the carbon, and that accomplishes dechlorination of the chlorinated solvents. And the technology behind this is that the activated carbon acts like a sponge with the contaminants. It really pulls them from the groundwater and the soil into the carbon matrix where they get treatment from the reagents that are included in there. We've had better luck with the BOSS 200 product for hydrocarbons than we have with the BOSS 100 product. So that's the one I think has probably got a little more acceptance nationwide. So that's been our experience with those two. But I do think that there's some neat applications of the trap and treat products going on right now. The other area where there's some advances going on is permeable reactive barriers. PRBs themselves have been around for a long time, and the idea behind a permeable reactive barrier is you install a wall of reactive material that as the groundwater flows through it, it's treated and you get clean water on the downstream side. Where there's been developments is how these things are being installed and some of the materials that are being used for the treatment. So this is a picture of a contractor from Michigan that uses a really large trenching machine. And you see on the photo on the left there, they've got this really big trencher. They can go up to 50 feet deep to install these permeable reactive barriers. And the advantage that you have is not only are they able to go deeper than traditional excavation can, but they also can install the reactive material right behind the excavation. So you can see on the schematic on the right-hand side, as it's moving from left to right, it's pulling out the natural material, and then reactive materials being injected behind. And so you end up with a one-pass installation to install a reactive barrier. So you need, you can get them into some tighter spaces than you can with traditional yellow iron type of installations. The other area that has been something new with PRBs is that they can be injected now rather than installed by excavation. And you see that done a lot with zero-valent iron nowadays. They've developed a nanoscale version of zero-valent iron that is much more injectable. And the other advantage of that type of ZVI is that it has more surface area and so can treat higher concentration plumes. The downside is since there is more surface area, it gets used up a little quicker and it has a less lifespan than some of the larger particle size ZVI. So we've gone through a number of advances in remediation technology in a pretty short time here, and have a couple of takeaways for you. And the first one kind of goes back to last week's seminar and reinforces that a detailed site characterization and a robust conceptual model is critical to getting successful remediation projects. Second takeaway is that there's lots of technologies out there, and there's no one that's the right one for every site. There's no silver bullet, and you have to really consider what the appropriate characteristics are of your site and the remediation. And lastly, you need to consider what the limitations are of the technologies that you're looking at and have contingency plans in place for any adverse effects that could come from them. At this point, we'll open it up for questions, and I think Alan has been collecting those.
Yeah, we have several questions from both sides of the border. I think the first one would go to you, Matt. Will thermal treatment work with NAPLs?
Yes, thermal treatment is effective at removing NAPLs. It doesn't have the same limitations of contact that some of the injection technologies do.
Andrew, the next one's for you. In regard to the ISCO technology, what are the limitations in using this technology inside a building?
There could be some limitations to access, so physical considerations. Actually getting a geoprobe or a drill rig into a building is usually the biggest concern. Apart from that, it is feasible. You can inject below a building. There's also angle drilling methods that you can come from the outside and access a plume. There's not too many concerns. You may want to pilot study doing it to see if you're going to release any of the volatiles into the gas phase to make sure that you're not going to increase the mobility of your chemicals and they could accumulate inside the building. So you could root that one out with a pilot study. But I definitely think it's feasible in most situations as long as you can get a rig in there and the equipment.
Matt, we have another question. Someone's just generally interested in state-of-the-art technologies for remediation. How would you respond to that?
Well, we've talked about a few of them over the last half hour or so, but you know, in general, there's lots of remediation options. Some of them have been around for a long time, and some of them are newer. And which one fits best really is dependent on your conceptual site model, and kind of goes back to last week's seminar about developing a robust conceptual site model.
Andrew, back to you. This one relates to the use of Plume Capture or BOSS 200, and in particular how the Ministry of Environment and Climate Change might view this particular technology.
We have employed the BOSS 200 and other in situ plume capture products at a few of our sites. I don't think we've used the actual Regenesis trap and treat brand. However, we have had some successes using these products, and they definitely are within the list of chemical injectants we consider viable for a multitude of sites. Regarding the regulatory permission to use these products, it would differ, I guess, from province to province or state to state, but the Ministry of Environment and Climate Change in Ontario is what he's asking about, and the ministry actually issues mobile certificates of approval to remediation contractors for the specific compounds and chemicals they're allowed to inject. So you could infer from this that this is permission for them to be allowed to inject these at sites. And typically they rely on a qualified person to monitor for any potential ancillary effects from the injected chemicals. So typically it starts with, if a remediation contractor does have permission to use these chemicals, typically the ministry is on board with it as well.
And to keep it balanced, Matt, we'll give one more to you, and this is the final question. It says, are there non-invasive or less invasive ways to remediate VTEX compounds, especially in groundwater that may have migrated towards public utilities?
Sure. As far as non-invasive, you know, I think your options are limited there to maybe monitored natural attenuation or possibly phytoremediation, depending on the site characteristics. But if you're talking about maybe something minimally invasive, some type of treatment zone near the property line might be the best way to approach that, where you know you may use a line of Waterloo emitters or an ORC type injection that would have some down gradient effects that would be positive on the part of the plume that has already left the property.
Okay, thanks. That's the some of the questions that we have at this time. So that will conclude today's webinar. Again, we appreciate everybody joining us. And if you have any questions, please feel free to follow up with either Andrew, Matt, or myself. And again, thank you for joining us today.